Thank you. I will explain all the words that are in my topic here. As we've said, my name is Konstantin Denisov. I am from Moscow State University. My scientific advisor is Alexander Viktorovich Shklaev. And I introduce you our results in low deviation of branching processes in random environment. So let me start with the problem of lower deviations. Imagine that we have some population that must grow exponentially. This model is more familiar to biologists. For example, green algae or rabbits in Australia obviously grows like an exponent. It's a known fact. But this model can be found in physics and mechanics. And then imagine that this population, for some reason, grows less than we expected. It also grows like exponent, but the less exponent you can see here. Like it's the real growth and this expected growth. The task of lower deviations is to find the probability of such event. Obviously, this probability tends to 0 when n tends to infinity. But the question is how fast it tends to 0, so what's the asymptotic of such event? Okay, let me introduce the model. We use the model of branching processes. Okay. And here is the famous Galton-Watson process. I think you are familiar with it. But we use some more complex model, the model of branching process in random environment. And I will explain what it means. Here you can see the definition. Let nu be the sequence of IID random variables. It would be our environment. And then let's take some family of generation functions that depends on some parameter like y. Then we define the x sub yj, ij, that are IID random variables with generation functions phi sub nu sub I with the fixed nu. So now x, y sub ij is not IID random variables at all, but they are IID random variables with respect to nu. And then we define that sub n as a branching process in random environment nu as with such formula. You can see that that formula is absolutely the same that for Galton-Watson process, but the only difference is with definition of x sub ij. Okay. Let me show you an example how it process may live and enlarge. For example, here we have one particle at start. Then the environment become, for example, good. For flowers that are drawn here, the good environment is sunny weather. So one particle gains many offsprings and everything is okay. Then the weather become cloudy, and some particles gain one offspring and some particles gain nothing. So it's obvious. Then the weather is sunny again, and the particles gain many offsprings, and everything is okay. But then the weather can be not just cloudy, but coldy, and many of particles just die out. So this branching process can die out at the start only because of bad weather. That's the difference between Galton-Watson and these processes. And then the weather can be sunny, cloudy, etc. Of course, if we have many particles, now the weather can't kill the process, so it will be okay, and the branching process will follow the weather. Okay. Next I want to say is that we will consider only the case of geometric family of generation functions. It's a very strong, it's very important for us, but here we need this consumption. We need this consumption because for these generation functions we have many theories like many theorems like aggressed effects that can help us to make our proof. And in fact, if you want to prove some statement about branching process, you need to first of all prove it for geometrical generation functions and then spread the result to all generation functions. So in my problem, there is no result for geometrical generation functions, and I need to make it first of all. Okay. Then we need to define some important thing, an associated random walk. You can see the definition of one step of this walk on the desk. It's a logarithm of derivative of phi sub nu sub I in point 1, and we define that its mathematical expectation is mu. Here, this sum is called associated random walk, and it is very important in analysis of branching process. I show it later, but now I need to say that we will consider only the case mu is greater than 0. It's super critical case, just quite the same that in Galton-Watson process, but it differs. Okay. Here there is the graphic that shows that our associated random walk are strongly connected with our branching process. Now we see the logarithm of number of particles in process and actually random walk associated with this process. They quite the same, you know. Of course, the number of particles in process are natural numbers, so the logarithm of it must be like a straight. But I draw it like a straight line because the associated random walk is more oscillating. Okay, so in a normal situation, our process will follow the random walk. So the random walk shows how environment goes up, and our process just follows it. Okay, now we can define what is the task of lower deviations. The task of lower deviations is to find this the asymptotics of these probabilities. You can see it here. It's the so-called integral asymptotic probabilities because we only want to know if z sub n is less than exponent of theta n. So of course, and if this z sub n not die out, so we need to be greater or equal to 1. Okay, the result for such probability was obtained by Bensai and Benhoff in 2013, and you can see it on the desk. And here you can see that there are two cases, in fact. There are two results, and the results is differ with some intervals that theta must be in. The first interval is m minus 1 to mu, where m minus 1 is some constant. You also can see the definition of this constant here, but all thing you need to know now is that the constant depends only on environment, first of all. Of course, this constant have its own meaning, but I can't explain it in such small time, so just the constant depends on environment. And in this first case, we have some result. And you can see that it depends on theta. But in second case, it doesn't depend on theta. And it might be strange, but I will show some graphics. Yeah. Да. Сейчас. Сейчас. Да, нам нужно... Сейчас берем логарифм от этого. Не, ну разве что Бенхоф ошибся. Ну, сейчас вот от этого возьмем logarithm divided by n, it tends to the same. Oh, sorry, yeah. Yeah. When writing, I forgot the logarithm. Of course, yeah. Logarithm, yeah. Okay. Yeah, this here must be a logarithm, so it will be okay. So you can see that in the second case, the result doesn't depend on theta. That is different from large deviations that you can see in lection of Gavril, for example. And my work finalized the results of Boenhoff and Bensai. Okay, let's turn to main result. For example, can I go here? No? Oh, okay. Let's Z sub n be our branching process in random environment with geometrically distributed number of offsprings. S sub n be its associated random walk, and xi sub I be non-lattice random variables. We need we need this because we want to use Petrov's theorem. I need and then let.
What does it mean, non-lattice?
Non-lattice, нерешетчатый, да. Non-lattice means that the values of this random variable don't lie in some lattice. Yeah. Okay? Yeah. And then let xi sub I also satisfy the Kramer's condition. Maybe somebody who familiar with large deviations know what it is. And it's just this condition. And then let k be some natural number that satisfy this condition. I'm not sure that is clearly seen from your place, but here we need k be such a number, so theta would be equal logarithm of k divided to n. Why it is so? Because we want to see the probability of z sub n equals to k. So it must be a natural number, and I can't write the z sub n equals to exponent of theta n. It's not a natural number, so I need to firstly to define k and then to define theta through k. So the first case is the case where theta is in interval m-1 mu. Here we need to take maximum because mu minus 1 can be less than 0, so it's easier to take maximum. Then we obtain such a result. Somebody can see that the result is quite similar for large deviations and for deviations of not of branching processes, but of deviations of random walk. It's also familiar. Yeah, but the only great difference is here the logarithm of k. It comes from our locality. Okay, yeah. I also don't talk about lambda because lambda is a rate function, and функция уклонений называется она. Yeah, people who know what is who knows about large deviations and other deviations know what it is. People who see the Petrov theorem know what it is, but now I can't explain it because it's too little time to understand where it comes from. So it's just a famous function. Okay, we have the first result, first case, and then we have the second case where theta is now between like 0 and m-1. Here we have maximum 2 because we need the theta be inside the interval of Kramer's condition. It's just technically, it's a technical thing here. So in the second case, we have another result. and you can see it here. And the first thing you can see, it doesn't depend on theta, even in constant. So it's quite strange if you think about large deviations, but for lower deviations, it just follows the result of Boeing-Hoff. It also can be similar to the first result in theta equals to m-1, but it's also a difficult thing. I won't tell you about this. The next thing I want to tell you is what happens in these two cases. Like, okay, we have formulas, but nothing is clear why such a thing happens and how branching process and its associated random walk growth in these cases. And there I have two graphics.
Sorry.
Yep.
If anything depends on NS here, on SM.
Yeah, in fact, the constant depends on Sn and S sub n, and S sub n depends on u, so the constant depends on u.
Okay.
Oh, yep.
In this formula, we don't have k. Maybe we should multiply it by e to the power of k? No?
Nope. K is also the theta. Like, if I put this a k, this would be depends on theta. Okay, well, Okay, the next result, the next thing is the graphics of trajectory of these processes. The first case is quite clear. We need the logarithm of our branching process reach the level of theta n, and this happens due to our random walk gets to this level. Everything is, I think, clear. So that's why the probability of such event is so similar to probability of events that S sub n reach this level. So the branching process just follow our random walk. And in the second case, the picture is different. Here, our random walk gets only to the level m-1n. And the branching process need to get the level lower than that. And if we have much particles, as I've said earlier, the branching process must follow the random walk. So the only place when this branching process can wait is the zero. Here, the probability of one particle gain only one particle is not so small. So our process like waits. When waits the point when afterward he can grow like our random walk. So here is all the gradient is also like the same as in random walk. Okay, why S sub n can't grow less than m-1n? I can't explain here because it's like inside the formulas and inside the proof. There is no the physical explanation is maybe too difficult for this. So that's our results. And at the end of my topic, I want to tell you about open problems in this area. And the first open problem is the behavior of this probability when the theta is near m-1. Obviously, there are some phase transition between these two cases. And if one finds the general formula for both cases, that would be a new result that can sum the results for first and second case. And then the next open problem is the behavior of this probability when the theta is near mu. Obviously, here we also have some phase transition, and here we can connect the lower deviations and the large deviations. And for the first case, it is in our plans for research, so maybe in a few years we get the result for theta is near m-1. Thank you for your attention. You can ask your questions.
questions?
I have a question.
Yeah.
Can you repeat previous?
Yeah, of course.
From previous slide? No. Next slide.
The-
Okay. Could you model the process in these cases?
How it will be, how it will be shown on the trajectory, like what the picture would be.
Yeah.
Mm.
We can model each excitation, and we can see how trajectory. We can see trajectory behavior.
Okay, like in computer, just model this process, yeah? Yeah, we can model it, and it will be like the same to this, because like it will be theta equals to m minus 1, and obviously it won't be need to wait the to branching process is to wait to random walk. So it be like that. There are differences because when theta n tends to m minus 1, there would be some difficulties with this random with the environment. There are some special things, but in general it would be like that. Okay. In fact, all special things will be only on the end of the random walk. Yep.
So more questions? If no questions, then let's send